Electrical Engineering and Computer Science from MIT in 2013. And next, he did a 2-year postdoctoral fellowship at Harvard Intelligent Probabilistic Systems Group, focused on the applications of deep learning and reinforcement learning techniques to healthcare data. He's currently the Director of Predictive Health Analytics at UC San Diego's Health and also an Associate Professor of Biomedical Informatics, where he leads an NIH-funded Critical Care Informatics Research Group. He has published in several areas of his research, including advanced signal processing, machine learning techniques, computational neuroscience, brain-machine interfaces, and predictive monitoring in hospitalized patients, which is resulting over 100 high-caliber peer-reviewed publications. The floor is yours, sir.
All right. Thank you so much for the invitation to speak here today. So I work with a number of people at UC San Diego and beyond. I also have a startup company. It's called Clarion. And so I do not receive any funding from this company, but I do get credit for some of the work that they do as well. With that, a bit about my background. Over the past 15 years, I worked across different hospitals and academic institutions throughout the United States. I started actually at University of Oklahoma. Back in the days, I was working on early prediction of tornadoes. This is early 2000 using machine learning approaches. Then around 2007, I moved to MIT. While I was at MIT, I was on a training grant at Brigham Women's Hospital. So I spent quite a few years around 2007, 2010, looking at healthcare data and thinking about how machine learning models can be applied for various tasks, including phenotyping patients, early prediction of disease. In 2015, I moved to Emory University in Atlanta. That's where I really got into this area of early prediction of sepsis. So for some of you who might be familiar with sepsis, it's a huge problem. 1.7 million Americans every year are diagnosed with sepsis. 1 in 3 people who die in hospitals, they die of sepsis. What we know is for every hour treatment of sepsis is delayed, mortality rate increases by about 7% or 8%, depending on which study you look at. So what is sepsis? It's essentially when bacteria gets into your bloodstream, and the immune system responds to that by producing pro-inflammatory chemicals into the bloodstream that causes leaky vessels and blood clots. As a result of that, the end organs, such as kidneys, livers, heart, etc., they may not get enough of oxygen and nutrients. And so patients with sepsis, they tend to develop what is called multi-organ failure. And at the time that patients, they develop multi-organ failure and are in a state of what is called septic shock, the mortality rate can be as high as 40% among those patients. In 2019, I moved to UC San Diego. I got introduced to Dr. Gabe Wardy by 2 of his mentors. Dr. Wardy, he's the chair of our sepsis committee, and we started really thinking about going beyond algorithm development and looking into deployment of this type of systems. So we published 2 papers. The first one is in 2021. It was in Nature Digital Medicine that introduced a new algorithm for early prediction of sepsis. The title says, artificial intelligence sepsis prediction algorithm learns to say, I don't know. And in a bit, I explain what that means. But really, the idea was to look into the performance of these models and figure out how to improve accuracy and reduce false alarms associated with early sepsis prediction. We didn't stop there. In 2024, we had another paper published in Nature Digital Medicine about prospective implementation of this algorithm, in which we demonstrated a 17% reduction in mortality. So let's jump into that right away. So this particular paper, it was about deployment of a system across 2 of our hospitals. In particular, UC San Diego at the time owned 2 hospitals. One of them is a Jacob Medical Center, which has 364 beds, and the other one is the Hillcrest Medical Center, 390 beds. What we did was we said, can we design a system such that as soon as patients step into one of these hospitals, we can get their data in real time and start making predictions about who is at risk for sepsis. So the system kind of looked like this. The electronic health record is sitting over here, and typically data from any type of diagnostic test that gets ordered, medications that being ordered, but as well as any type of information that gets written into EHR through nursing assessment of patients, etc. Through what is called integration engine, it lands in electronic health record, and there is a protocol for data access. It's known as HL7 FHIR that allows us to access that data in real time. This particular protocol, you can think about it as just a API. With the right authentication, you can ask for a specific data elements for patients. You can say, I want to know what is this patient's vital signs, heart rate, blood pressure at the current time. I want to know also what was the history of this patient. I want to bring all the clinical notes. I want to bring all the diagnostic tests. I want to utilize that to make predictions. So we managed to access that data and push it in real time to Amazon Web Services. Within the Amazon Web Services, the composer algorithm, this is the first paper that was published in Nature Medicine. It's running there and is able to analyze that data, generate risk scores, and then through what is called the HL7 data interface, send that data back into electronic health record. Once the data is back in electronic health record, and this happens pretty much at the level of minutes, we managed to generate what is called a best practice advisory. It's a pop-up for nurses who, roughly every 15 or 20 minutes, they might log into the patient chart. If the patient's risk score is above the threshold, they might see one of these pop-ups. The pop-up describes basically the progression of patients from early signs of sepsis that has to do with things like fever, increase in heart rate, increase in respiratory rate, all the way to development of severe sepsis, which, as I mentioned, is associated with organ failure and septic shock, where the patient becomes severely hypotensive. The pop-up tells a nurse that this patient is at a risk for the next 4 to 6 hours. It also displays information about why the algorithm thinks this patient is septic. It could be things like, vital signs are abnormal, or the patient's, white blood count is abnormal, etc. So in response to this pop-up, the nurses, they had the option to do one of the followings. They could select to say that I will notify the MD immediately. And the reason they may want to do that is because medical doctors can order antibiotics. As I mentioned earlier, antibiotics can be quite life-saving in patients with sepsis. They also had the option to say sepsis treatment or workup is in progress. It means, yeah, we have some suspicion and we are working on it. Potentially in that scenario, the alert actually increases their post-test probability, and they might accelerate things such as ordering antibiotics. They also had the option to say no infection suspected. It means the algorithm really doesn't know what it's talking about. Or in some cases, they could actually close the pop-up altogether. So that's the 4 different options that they had. So in our paper, we did what is called a causal impact analysis, which is a form of time series analysis, where the algorithm was deployed in December of 2022. That's the vertical line that you see over here. So you look at the historical data, and you essentially fit a time series model to predict mortality. This time series model makes use of patient-level information, but also things such as seasonality, volume of patients in the emergency department, and many other factors. And then after the intervention is implemented, you run it forward to make predictions. So the dashed line here was the model's prediction for what the mortality rate should be. The solid line is what we observed. If you subtract the 2 and take the cumulative sum, it basically shows a reduction in mortality. When you do the calculation, it turns out it was about 17% reduction in mortality, which was associated with 10% increase in timely utilization of antibiotics and other life-saving treatments. So we digged into the mechanism behind this, and we realized that if you look at the here is showing the data for a few months. If you look at the nursing actions, roughly 60% of the time or so, the nurses, they said, will notify MD immediately. There was another 5% they said workup was in progress. A few percent they said no infection was suspected. I think it's about 20% or so. And then in less than 5%, they said no acknowledgement was given. When we did the analysis with this data, we realized that after adjusting for confounders, this is in a multivariate regression analysis, anytime that the nurses selected that they will notify MD immediately, there was a significant reduction in time to mortality, significant time to antibiotics, which then translated in reduction to mortality. So we propose that as a mechanism for why we observed the reduction in mortality. We received quite a bit of press coverage for this work, including, Fortune magazine, the Bipartisan House Task Force on AI mentioned this work as an example of AI that can save lives. One of my favorite actually write-ups about this work is an article by Professor Joseph Kevadar, the editor-in-chief of Nature Digital Medicine, where he basically says that deploying AI into healthcare systems is more than just algorithm. And I borrowed that as a title of my talk, and the rest of my talk is really about how do you go from algorithm to deploying systems into health systems. So deploying of algorithms, they have actually a very nice table. Is their table 1 in this editorial, where they lay out exactly what are the steps that needs to be taken. So the first one obviously is data. You need to have data that can be accessed in real time if you're interested in real-time clinical decision making. The second one is infrastructure. This infrastructure needs to be capable of managing potentially across thousands of patients that type of data and allow for deployment of algorithms. You need to have interfaces that you can use to send and present that information to the end users. In this case, in our case, was nurses. And then you need to identify the appropriate, identify the appropriate, end users. Are they, clinicians? Are they, nurses? And then also figure out how to establish trust with these end users. Because, as I talked about that, the pop-up that we presented to these nurses, they could have easily closed it. So why is it that, they decided not to do that and follow? So understanding your end users, figuring out what level of education you need to provide to these end users, but also, how you gain their trust over time, it turns out to be very important. And then there is this notion of alert fatigue. For anybody who has been into an emergency department, or if you have ever watched, Dr. House, you know that in clinical environments, there are a lot of alarms that are going off all the time. That's the notion of alert fatigues. So getting above that noise level and convincing physicians that this is important and can be potentially a life-saving, that's also important part of implementation. And then really figuring out the clinical context, what can be done after you send an alert to an end user. Is there enough of staffs available to take the next steps, initiate antibiotics, assess the patients for, hypotension in our case, and figuring out if the patient needs fluids resuscitation or other steps. And then finally, even when the system is in place, after deployment, monitoring the system over time is very critical, because we know that the characteristics of patient population change over time. The data source that is fed to AI can change over time. So monitoring the AI for its performance and then taking corrective actions is super important. But also on the top of that, monitoring end users. So I'm going to walk you one by one into each one of those. So let's just starting with data. Over the past 10, 15 years, we have been hearing about big data. So big data, it comes into many different flavors. You could have basic demographic about the patients, information about things like social determinants of health, financial informations. You could have contextual information about the patients. What is their medical history? What are the sort of exposome environmental factors that is influencing them? And then diagnosis, interventions, you can go deep, into the world of omics. You could also look into imaging. And then, with the advent of large language models, now it has become so much easier to do a deep dive into unstructured clinical notes that are available about the patients. And then, physiological data. These are data that are generated from bedside monitors or wearable technologies, etc. So the key value proposition is that AI allows us to integrate really diverse data types in order to make timely predictions and improve situational awareness, either at the bedside or even once the patients leave, they go home, being able to identify patients that are at risk for deterioration and monitoring them is super important. And then, AI also helps with personalization of care. Sepsis is a prime example of that. Sepsis is a syndrome. It's a very heterogeneous, condition. Patients, they come in with many different signs and symptoms, and being able to phenotype that and personalize the care is super important. And then the other part, which I will not talk about so much, is about optimization of care protocols. This falls into what in electrical engineering we call it control. In machine learning is called reinforcement learning. It's about sequential decision making and optimizing treatment protocols. So those are some of the value propositions. What are the limitations? Well, for most part, data in healthcare still remains very siloed. And also, as you go from one healthcare institution to another healthcare institution, the format in which data is stored might not be interoperable. So you might build the algorithm for one hospital, you go to the next hospital, and it may not work right away. The next one is this issue of, one of my mentors calls it DERTA, the idea that data in electronic health record, but even data that is recorded through various type of sensors may not have the right quality. And if you fit data with low quality to AI algorithms, you're going to end up with false alarms and incorrect predictions. And then the other issue is, which is very much pertinent to data in electronic health records, is that big data doesn't really mean timely data. Medicine traditionally has been very reactive. So you may have a lot of data, but it may not help you with prediction. And that's why it's so important to have continuous, sensor data, and which I know is one of the key strengths of, the Terasaki team. So beyond data, we need to think about infrastructures. I talked a little bit about the infrastructure that we have. Essentially, what is happening is there are existing systems that allows for integration of data from bedside monitors from various type of devices into electronic health record. And then once the data is available to an electronic health record, there are ways of standardizing data. FHIR is one of those protocols that provides a standardized language, essentially, for accessing that data. So how does it look like? So a typical FHIR resource is in the form of a JSON object, where, so in this case, I'm showing an example of requesting, systolic blood pressure. In terms of data harmonization, what FHIR does, it makes use of standardized codes, things like LOIN code, SNOMET, other factors, in order to make sure that when we talk about a piece of data, in this case, let's say systolic blood pressure, across different scenarios, it's the same exact type of data. I'm using the example of systolic blood pressure here because even with something like blood pressure, depending on which site of the body, whether you are measuring at the wrist or upper arm, different locations, you may end up with different values. So the standardization here with things like LOIN code gives you that level of specificity and allows you to harmonize data across different health systems. So the way FHIR is set up essentially is a set of standardized for representation of data, and also a set of APIs that allows you to access that data in real time. So that's what we have done with the system that we developed here at UC San Diego. We connect to the electronic health record, we make FHIR calls on an hourly basis, And then we structure that data, extract features, and then pass it to the deep learning model. And the system is built within the AWS, so it's scalable. You can have n different algorithms. You can calculate the risk scores. And once you do that, the way you get the information back into electronic health record is through another protocol called HL7 v2. This is the same protocol that manufacturers of bedside devices, such as like Philips, GE, etc., they send information into EHR. Again, it's a fairly ancient standard, HL7, but it allows you to define like your observations. What's the risk score? What's the confidence interval? What are the sort of top contributing factors? This is a notion of interpretability of AI. And it allows you to push all of those into EHR, which lands eventually in what is called a flow sheet. And once the data is available in EHR, any other types of user interfaces, they can make use of that data to alert clinicians, etc. So if you go even one layer sort of below within the AWS, there are tons of resources available for building platforms that are fault tolerant. Why is this important? Is because when you're building systems for clinical applications, you need to have 99.999% uptime because people are relying on your system to make decisions. So what we did was we basically made use of technologies within AWS, things like what is called auto scaling and load balancing, to ensure that the system that we have running, they have very high uptime, and anytime for whatever reason, if they go down, this technology allows us to bring back the system. Similarly, with all the databases that we use, they are also have redundancies built into them. So there are backup databases. So if any of those databases goes down, they automatically are brought back, or a copy of those are brought back. So in that way, we can really minimize the downtime associated with this type of systems. So these are some of the sort of efficiencies that you gain by going through the cloud implementation. In addition to that, if you're interested in like scalability, cloud provides systems such as like within Amazon, we have something called Amazon Lambda, which is essentially a way of containerizing your application and essentially making a function out of that. So in this case, a composer becomes a function where it has a number of inputs, the inputs being labs, vitals, demographics of the patient, etc. And then it has the output being the risk score, the top causes, etc. This is the notion of serverless computation within AWS, where once you define a Lambda function, whether you have 10 patients or 100 patients or 100,000 patients, you can simultaneously invoke your Lambda functions to do the computations, or in parallel, it might take 5 minutes. And at the time, you just pay within the AWS for that 5 minutes, and then it's being brought down. So it's very efficient and it allows for scalability. So that's in terms of a little bit about the infrastructure that goes into building these type of systems. And then in terms of addressing multimodal data, a lot of our work over the past couple of years was about, okay, we have access to EHR data, but can we bring in DICOM images? Can we bring in things like Fitbit data? We actually have an agreement through a research agreement with Fitbit, where we are able to call the APIs and bring that data. And we have a couple of papers, you can look them up, where we make use of this information in an outpatient setting to make prediction about like readmission. Similarly, with things like social determinants of health, bringing that information with the help of natural language processing, large language model, extracting critical information from those and adding them to the algorithm. And then more recently, we started looking into things like microneedle sensors. Dr. Joseph Wang at UCSC has been doing a lot of pioneering work in this area. There are also continuous monitoring type of systems that are becoming available through industry partners, etc. And then going deeper with respect to omics and mRNA type of systems, we have a study ongoing right now at UCSC where we are working with informatics, and we get their data into our cloud system in order to make predictions. So as you see, increasingly, these type of systems are becoming multimodal. So a bit about the algorithm that we used for this particular deployment at UC San Diego. So the typical machine learning models are based on data from, let's say, hospital A. You pass it through a deep neural network and you make a prediction. At the time of deployment of this type of systems, there is very little quality check. This particular algorithm is making use of what is called conformal prediction. The idea is that during the training of the model, you keep track of examples of, in our case, septic and non-septic patients where the algorithm performed very well. When it comes to prediction, a test patient, a new patient is provided to the system. The first thing that the system does, it actually makes a comparison of the input data against all the examples of historical data that it has seen that was able to make correct predictions, and only makes predictions if it's able to find similar examples. Otherwise, it goes ahead and rejects that sample. So the reasons for rejections, it could be because the data is low quality, or the algorithm is seeing a new patient that has never seen in the past. In those cases, the example gets rejected, and then the question is, what is the next step? Sometimes the next step is to check the data quality. Sometimes the next step is to order additional diagnostic tests. Sometimes the next step is to retrain the algorithm with the new, types of patients that the algorithm is seeing. So utilizing this approach, we demonstrated significant reduction in false alarms. In particular, we showed 5-fold reduction in false alarms after deploying this system. And this is across emergency departments and ICUs across 2 different hospitals. So I already talked a little bit about, user interface, but, physicians at the bedside, they are super, super busy. Catching their attention is not easy. So because of that, deploying this type of system requires a lot of education, really bringing it to their attention. So again, the particular way that we caught their attention was through these best practice advisories. But even that, we had to do 6 months worth of training of our nurses. And even that is not enough. Like places like UC San Diego, we have a lot of traveling nurses, new people coming in during the summertime to enjoy the beach. And so this issue of end user and education of end user becomes pretty much a continuous part of deploying AI systems into practice. And then monitoring. As I mentioned, once you deploy the systems, you need to have dashboard to monitor the performance of this level of system. So here, this dashboard is showing sensitivity and positive predictive of this model across time. But also every component of the system, including all the databases, everything else, we needed to have monitoring built into those. In fact, I have engineers in my team where they have what is called pager duty. It's a system that anytime, 24/7, if the system goes down, they have to go and log into the system and figure out what is going on to ensure that the system has a very high uptime. So post-implementation monitoring of the AI system as well as the platform is super important, but it's not enough. So, with algorithms, we have ways of fine-tuning them if the performance goes down. And there's like a few papers, if you're interested, you can read about our work on what is called transfer learning. With humans that are ingesting and using this information, it's also important to monitor their behavior and see what is going on. So in particular, we conducted a survey of physicians right after implementation of our system. And we try to assess their attitude towards the algorithm. And what we noticed that essentially providers who had 0 to 5 years of experience versus providers who had 6+ years of experience, the first group, they had significantly higher, positive attitude towards, utilization of AI models. So there is a whole generational component to gaining trust and getting end users to comply with this type of systems. In terms of monitoring, we also have systems in place to look at the, I mentioned earlier on, the nurses, they had 4 different actions. will notify MDs immediately, or saying that the sepsis treatment is in progress or no infection suspected. So we are able to look at what percentage of time over time you're selecting each one of these options. In particular, you might observe a pattern here in terms of no infection suspected, that the percentage of time that they were saying that no infection was suspected after receiving an alert actually went down since like summer of 2024, which I will get into in a bit. It was because we deployed a large language model that was able to read through the patient's clinical notes and get rid of cases of alerts that were not due to true infections. So I'm briefly going to talk about this notion of timely data, that I touched upon a little bit earlier on. And this is highly pertinent to you guys who are building continuous sensing sensors. One of the central problems that we have in healthcare is that data is reactive. So here I'm showing the timeline of a patient. This particular patient at 8 a.m., there was a set of vital taken on the patient, and the temperature was slightly elevated. But this patient was in a hospital ward setting, and there was very little monitoring. Several hours passes by, and then a nurse realizes that this patient's blood pressure is very low. So this patient at this time is hypotensive. They order some labs. Once the lab results come back, the risk score jumps to 81. All right. So, we often talk about, early prediction. For many of these type of AI systems, they talk about early, predictive analytics, right? But in practice, what we get is delayed prediction. And the reason is because we don't have continuous monitoring in place for most part. So in healthcare, you get data when there is some clinical suspicion by nurses or by providers. That's when they order the labs. And because of that, most of our predictions, they end up being delayed. So this notion that AI is essentially looking over clinicians' shoulders, and whenever clinicians, they have some suspicion, that's when, the AI system comes in and makes use of the data that is ordered by the clinicians to make predictions. So I'm going to skip through here briefly. And, so how do you go about addressing this issue? We had a paper, it was a commentary published in Critical Care Medicine that essentially said, if you look at the way, AI systems, they get implemented. So there's the IT infrastructure, there's, artificial intelligence layers. There are some policies that hospitals, they put in place. But then there is what I call the behavioral layer. This is where the caregivers, they get involved. And then caregivers are the one who are involved with data generation in typical sort of scenarios. So one of the questions that we had was, is there a way for AI to get involved in data generation? If the data that is available through EHR is delayed, is there a way to get the AI to essentially submit orders for labs, etc.? So we did a study, actually. We looked at cases where physicians initiated antibiotics. So that's the time of antibiotics. This is the time of suspicion. And we looked at when there is evidence of organ failure. Sometimes the evidence of organ failure happens before time of clinical suspicion by physicians. Sometimes it happens after. We asked the question that whenever it is happening after, is there a correlation with lack of availability of data prior time of clinical suspicion? And in the paper that is published now in Journal of JAMIA, we found a strong evidence that often when the time of organ failure is after time of clinical suspicion of sepsis, prior to that, there was very little data available. And so the recommendation that we had was so much of clinical diagnosis and decision-making is about making use of data. But, if you don't have the data, then it's a problem of, unknown unknowns. So is it the case that this patient had, sepsis earlier than the time of clinical suspicion? Or is it because you just didn't have the data and you weren't able to make any assessments? So in order to address that, we came up with a design where the AI system makes a prediction, upfront, but then it assesses the degree of data missingness along the way. And if there is data elements that are missing, then it activates various type of pop-ups in the EHR saying that, there's a suspicion that this patient might be, moving towards becoming septic, but we don't have timely blood pressure measurements, let's say, dear nurse, can you give us a nursing assessment here? Similarly, as you move towards it, along this diagnostic pathway, by the time you get to severe sepsis, you need to have timely labs. But if the labs are missing, the system can send, additional pop-up asking the nurse to order that. So we have this currently going on at UCSC. We started a pilot trial of this system earlier in January. But there are challenges. Whenever you introduce new, innovations to healthcare, you have to think about who is going to pay for this, and who can actually do this. In terms of like diagnostic tests, only physicians, according to CMS, they are sort of empowered to determine what is reasonable and necessary to order diagnostic tests. And then there are tons of other issues, such as liability-related issues. If you order diagnostic tests, somebody has to look at that. Like if you order an AKG test, you need to have a cardiologist to look at that. So there's issues such as that. So with all of that, in view, I think one of the key areas of opportunity is, continuous data. And as I mentioned, we started looking at some of those continuous data, such as like wearable sensors, body-worn patches that provide continuous measures of vital signs, etc. But also more recently with this sort of microneedle sensor technologies, this group, you guys are working on this, ocular lab. Any type of continuous type of data that we can introduce is going to be very, very helpful in this context. All right, with that, I think I have about maybe 5 minutes. I wanted to go back to this issue of uncertainty. And one of the reasons for uncertainty is often a lot of signs and symptoms of patients, they overlap. So at the time of presentations of patients to emergency department, to hospital, just based on the available data, often it's very, very hard to say, what's going on with the patient. So in particular, with sepsis, there are a number of 25 different conditions that are known as what is called sepsis mimics. Sepsis mimics, again, there are conditions that, patient may come in, may have elevated heart rate, elevated blood pressure, maybe a bit of temperature, but the patient may not be septic. It might be a sign of acute like liver failure, or it might be a sign of alcohol withdrawal, or a number of other conditions. So over the past year, we have been thinking through this notion of diagnostic uncertainty. And the solution that we came up with is based on use of large language models. So we have our algorithm, as I mentioned, the composer algorithm. This system connects to EHR through FHIR. It makes predictions. If you think about risk score, here the x-axis being the risk score or the threshold that is being used in the risk score, depending on where you put the threshold, you could end up with different positive predictive value versus sensitivity. So if you go, if you increase the threshold, then you start having higher positive predictive value, but that comes at the risk of reduction in, sensitivity. So the solution that we came up with, we basically said we are going to look at all the borderline cases. These are the patients that it's not really clear yet whether they are septic or not. And we're going to do a deep dive into these patients. The way we do that is by extracting all of their clinical notes from the electronic health record using, again, FHIR. This happens in real time. And then we pass it to a large language model to extract a specific sign and symptoms. Then we perform differential diagnosis. And then we send an alert out if only sepsis is among the top factors among these patients. So how does it look like in practice? So here's a sample clinical note for a patient. I'm sure everybody here has interacted with large language models, so you can actually come up with a prompt saying that, let's say you are a ED doctor, you're in charge of identifying signs and symptoms, such as, potentially positive COVID-19 test or fever or elevated lactate. We do that, and we are able to get the results back in a structured format, either as a list or as a JSON object. We repeat that for about 200 different observations about the patients. Once we have that set of signs and symptoms, we design clinical calculators. These are essentially Bayesian reasoning calculators, where they assess the likelihood of every one of those sepsis mimics that I mentioned, the cirrhotic patients, heart failure patients, alcohol withdrawal patients. So we end up with a list of about 20 of them, and then we sort that list, and we only send alert out only if the sepsis is within the top 5. What we have demonstrated is once we do that and we have this sort of alternative diagnosis, in terms of performance, our positive predictive value, which previously was about like 22%, jumps up with this approach to about 52%. In some of our recent work, we have been able to push it to closer to 60% or so. One of the key questions is, if you do this analysis using retrospective data, in real time, do you have access to similar notes? Because anybody who is familiar with clinical workflows, they know that physicians, they don't write their notes always in a timely fashion. So because of that, we were able to prospectively deploy the large language model and do a prospective study. And we also observed a significant improvement in positive predictive value utilizing a combination of predictive models plus large language models for kind of looking at the patient history, et cetera. Let me skip through that. And as I mentioned earlier, this is the reason we observed this reduction in a proportion of times the nurses are selecting that no infection is suspected, because now the system is able to really do a deep dive and assess other potential explanations for abnormal signs and symptoms that we observe. We perform causal impact analysis here to see if there are other factors are able to explain this reduction, and we were able to show that the pattern is also significant here. So again, this is a nice example of a system, AI system that is already in production, and we are able to monitor the system pretty much on flight, change the system by introducing new technology like large language models, and then monitor the performance after deployment, sort of to continuously improve the system over time. All right, with that, I'm going to wrap up my talk. This is a quote. I asked ChatGPT about what a modern Tolstoy would say about data science and working with data abstracted through electronic health record, and basically saying that data alone cannot tell us what is good or evil. In particular, when it comes to patient care and patient wishes, it's very important to have physicians at the bedside in order to really listen and talk to patients and family members to see what their wishes are. So in that context, really the ultimate goal of AI is to streamline analysis and ingestion of multimodal data to simplify things so that clinicians can spend less time with documentation, less time with multimodal data integration, and spend more time with patients. Okay, here are some of my sources of funding. I've been lucky to get funding from NIH as well as industry partners, and we have been working on a ARPA-H proposal together. I'm really looking forward to have that proposal funded so we can kickstart a collaboration together. At this point, I'm happy to take any questions that you have.
Thank you for the fantastic talk, Professor. A couple questions came in. One of them is, thank you for the great talk. Are there any particular reason why you chose AWS as part of the infrastructure over other cloud service providers like Microsoft Azure?
Yeah, that's an excellent question. Actually, I started working with cloud around 2015. At the time I was at Emory University, Google Cloud, they came to us, and so we worked on one of the first applications with what is called their healthcare APIs on the Google Cloud. When I came to UC San Diego, they were already working with AWS. And I think AWS has done a really amazing job of working through all the healthcare regulations and doing a great job on the governance side. So I can say on the technology side, I think there's still a lot of advantages, let's say, to Google Cloud. they are really doing advanced work with their foundation models for many other things. When it comes to healthcare regulations, HIPAA compliance, ensuring security, etc., Amazon has done an excellent job, and because of that, UC San Diego was comfortable working with them. So it really comes down to healthcare regulations in this case. Having said that, so much of what we do is cloud agnostic. On the operation side, like hospital side, at UC San Diego, we are also working with Azure. In particular, Azure is integrated with Active Directory and all the systems for login, etc. So it has some advantages.
Thank you. Of all the challenges you mentioned, which one do you think is the biggest hurdle for effective implementation of your sepsis prediction system?
Oh, it's healthcare. You want to solve one problem, you have to solve 10 problems in order to solve that one problem. But I think, we have made a lot of progress on the technology side. I can tell you, when I first started with this type of deployment, you needed to have a team of at least 10 HL7 engineers to help you with integrating various type of data sources. So data sources are, traditionally are very siloed, bringing all of them together. With the introduction of FHIR and other types of interoperability standards and layers on the top of EHR, now integration problem is much, much less of a problem. I think we are at a place right now, we have access to cloud. We can do a lot of this work on the cloud. We have data standards, again, with APIs for accessing variable data, etc. I think at this point, the biggest, challenge is building systems that actually end users, they like and trust, because it's still the clinicians cannot wrap their head around the complexity of deep learning models. Even though there has been a lot of progress on opening the black box, I'm sure you guys have heard about Shapley values, all of these interpretability methods. The explanations that these systems they provide is not at the level that clinicians they conceptualize and think about these problems. Clinicians they think about more of a systems level, versus AI comes back and says this patient's heart rate is abnormal. How do you go from there to contextualizing that and getting to the systems level so that physicians they know exactly what to do? So crossing the gap between prediction and actionability, that's still a big challenge.
Thank you. With recent advances in regenerative AI, there has been a surge of interest in using large language models. Where do you think we are going from here in terms of clinical implementation of these large language models?
Yeah, I think at UC San Diego, currently there is a lot of work on generating like auto replies to patients' inbox messages. So there is some of those are sort of low-hanging fruits going on. When it comes to diagnosis and treatment, I don't think the AI systems are yet there. They're getting very close. The key challenges there are, there's a lot of work with retrospective data. When you start thinking about real time, you have to think about availability of data in real time, right? So if you don't have the data available in a timely fashion, you won't be able to leverage large language models. So the way we leverage the system is purely for information extraction. So with our differential diagnosis calculator, we use it essentially for, if you're familiar with NLP, for named entity recognition, finding the right signs, symptoms, other confounders. You could go and straight ask a model such as GPT-4 or Cloud Sonnet 3.5 to perform differential diagnosis, but in our experience with real-time data, we did not have good experience with those type of things. But I'm sure it's moving in that directions, because now we have ambient transcription type of technologies where they are listening to physicians in real time and doing the transcription, and then that can be pushed in a timely fashion to large language models. I think once we get to that point, that we have that data, then we can do a much better job with large language models.
One final question. With the acquisition of data from sepsis or other patients, do you think there's a security issue where people can access when they're in the cloud system?
Yeah, really good question. So when you work in one of these environments, you realize that it's really, really locked down and secure. My engineers, the first couple of weeks, they feel shocked because they realize they don't have access to internet. If they are, something as simple as importing a Python library, they cannot do it because the system is locked down. There is no connection to internet. So we had to create our own local Python repo for things like that. So the systems are very much locked down. On the top of that, you have audit trails for everything. And then on the top of that, often there are insurances put in place. Like if you're a vendor working with UC San Diego, you need to have a $10 million insurance. And you need to indemnify the university or the health systems for breach of. So there's a whole lot has been done over time to secure the type of systems, putting controls in place, and then at the end of the day, it's always a trade-off. You're taking some risk, and you have to be accountable in case of a breach. So it's never about completely mitigating the risk. Is about how you manage the risk.
I see. Thank you. Different data sets have different quality. How do you solve this problem when using them together?
Yeah, that's an excellent question. A lot of my earlier work actually was on working with sensors data. And in that context, we always start by developing signal quality metrics. So some of my earlier work with electrocardiogram, we had to develop quality measures for AKG. Similarly with respiratory signals. With electronic health record data, there are reference ranges for all the labs. Having said that, nurses, they can make mistakes. And that's why we developed this conformal prediction framework. Essentially, as I mentioned earlier on, is a way of detecting outliers and rejecting those outliers. So you have to kind of build all of the safety steps into the system. So yes, data quality is super important. Always checking the reference range is super important.
Well, that's all the questions I have. Thank you for your time, Professor. I appreciate it.
Sure.
Have a
Thank
nice
you for
day.
listening. Okay.